I want to talk about one more phenomenon that has to do with electromagnetic waves in this video, and it's called polarization. Now, this is a different polarization than the kind of polarization we learned about when we first started learning about electrical charge and electrical force. This polarization is so we talked about how in just a basic electromagnetic wave we have the E wave, and I'll draw it nice and sinusoidal. That's the E wave. And then the B wave is in sync with it and perpendicular. So I'm drawing this because it's sort of coming in and out, right? So this is the B wave, this is the E wave. And so actually the way I drew this, this would be going that way. The wave would be traveling that way based on the right-hand rule. And so if you had a charge, say an electron, that was oscillating vertically up and down, right, then that might create this. That might create an electromagnetic wave like this. Okay. That's one electron vibrating up and down, creating creating a wave going out this way. By the way, it would also be going out in the other directions too. But what I want you to think about is, what if you have a whole bunch of electrons and they're vibrating in all kinds of different directions, right? And they're going to be sending electromagnetic waves in all directions, but also notice that they're kind of oriented in different ways. So the electromagnetic wave that's heading out to the left here there'll be like multiple waves on top of each other oriented in different ways. All right, different picture. Let me redraw this. Imagine that you're looking head on into the wave that's coming at you. All right, so you're looking head on into the wave that's coming at you. So you might see one wave. So this is the E field going up and down, coming at you. Of course, the B field then is going left, right, but I won't draw that, okay? I'm just going to draw the E field. But maybe another electron is going like this. So the E wave is going up and down as it comes right at you. Remember, you're looking straight down the gun at this. And maybe there's another electron that was creating a wave that's going like this, and another one that's going like this, and another one that's going like this, right? And so depending on the source, if the source is just made up of randomly oscillating electrons or other charged particles, you're going to get mixtures of waves that are oriented in all different ways. And this is called unpolarized waves, or I'll just call it light, unpolarized light, because it's made up of all different orientations. When you only have it going in one direction, that's called polarized. It doesn't have to be up and down. It could be some other direction, but if it's just one direction, that's called polarized. And remember, I'm just drawing the E. Remember, for every blue E line I'm drawing, there's a perpendicular green B wave that is also there too. Okay, so that's what I have written up here. So E and B fields produced by each are oriented in various directions. These are unpolarized waves. Polarized waves are waves in which the E and B fields are each going in one direction only. Okay, so you can make polarized waves from non-polarized waves. Also, you can change the direction of polarization even if it's already polarized. So there's something called a polarizer. And a polarizer is like a filter. Often it's just a circle. And without getting into too much detail, imagine it's got like sort of a grating that's oriented in one way. So there are actually chemicals, long molecules that are going all in one direction. And when unpolarized light comes at this, coming through here, and imagine this is coming from behind, and then it passes through here, and then it comes out the other side. These long molecules actually can absorb any of the electric field that's going its way vertically. So it actually absorbs the vertical one, and the ones that are like kind of diagonal, that are partially vertical, it absorbs the vertical components of those. So anything vertical in this will be disappeared. It'll get absorbed by this polarizer. And so then what comes out will be all horizontal. So it'll go from unpolarized to polarized. Okay. Now, of course, in doing so, it had to absorb a lot of the light, I'll say light, which means it took away some of the energy. It absorbed some of that energy, which means the light that comes out will be less intense, right? Because intensity is a measure of energy. So the price you pay for polarizing it is that it's going to be a little bit less intense. For actual visible light, it'll be a little bit dimmer, right? Okay. Now, if you go, how much dimmer? That's the question. So actually, I have two things here, and let me talk about the second one first. If you go from unpolarized to polarized light, it turns out that the intensity gets cut in half. So the final intensity is 1/2 of the initial intensity. Okay, so that's the situation I drew here. Now, what if you have light that's already polarized, maybe at like an angle like this, and then we send it through a polarizer, and then it comes out. Of course, it has to come out polarized the way the polarizer wanted it to be, which is perpendicular to those molecules. Okay, so again, it's going to be sapped of some of its intensity, and it turns out that in this case, when you just go from polarized to differently polarized, what you do is you multiply by cosine squared of the angle between the two. So like if I kind of superimpose the initial one on top, and we just look at that angle, that's theta. So the angle that it like switched to, that it went from this to this, you multiply by the square of the cosine of that angle, and that's going to be the new intensity. Notice that's always less than 1, so yes, you get a lower intensity. And this is called Malice's law. So these are the two laws that govern polarization. So let's finish up this topic with just an example of that. Suppose we start with unpolarized light, and here's its intensity, and it passes through a polarizer that's oriented horizontally. Then we have two polarizers in a row. We then pass it through a polarizer that's oriented 10 degrees from horizontal. So what will the final intensity be? All right, so we have two polarizers. Sorry, just switch those to black. And this polarizer, I guess the molecules are vertical because light coming out of it will be horizontal. And then this one, the molecules are different, and it's always going to only let light come through that is polarized 10 degrees to horizontal. So we start with unpolarized light coming in, and it comes through here, and now it's just going to look like this, and then it comes through here, and now it's going to be oriented that way. Now the initial intensity, when it passes through here, now unpolarized to polarized, is going to be half as much. And then from here to here, we're going to multiply by cosine squared of 10 degrees. So we're using both laws here, unpolarized to polarized, and then polarized to differently polarized. All right, and putting in the 28.0 watts per square meter, that was the original intensity coming in. When you multiply by a half and then by the square of the cosine, you get 13.6 watts per square meter. Okay. So when I see you in person in class, I will actually show you polarizers. They're just small little discs that are, nothing strange about them, and I'll show you how they work. We'll shine some light through them, and you'll see what they do. By the way, I should say that your eyes don't necessarily have the ability to tell when light is polarized. It looks the same to you. Of course, you can tell if it has less intensity because it's been polarized, but you don't see anything different. But I'll still be able to show you how it works. I'll show you a little demonstration that shows that the intensities are changing when we pass light through it.